Welcome to the Foundation Lectures on NST. My name is Herwig Mannaert, and in this first part we look at the grounding of normalized systems theory in systems theory and stability by considering the design cycle of artifacts as a dynamic system. Now, the research on normalized systems theory started a little bit more than 10 years ago, when my colleague and myself started wondering why software systems were so problematic to change, were so difficult to change, and which seemed even to get worse over time. Now, we discussed this with many practitioners, and most of those practitioners agreed that this was probably the single most important problem in software systems. So we asked ourselves whether such progressive structure degradation could be scientifically described and maybe in that way even be controlled. Now, there is a concept in engineering describing something which gets worse over time, which is progressive. And that concept is a dynamic instability due to positive feedback. Now, probably the best known example of a dynamic instability due to positive feedback is the collapse of the Tacoma Narrows Bridge in the 1940s. And though that collapse was caused by a positive feedback, an instability due to a positive feedback mechanism between the wind and the motion or deflection energy of the bridge. Now, there are many positive feedback mechanisms, and the one that destroyed the Tacoma Bridge is not the only example. So, for instance, if we look at a single swing or hammock chair, it's also an example of positive feedback and a possible dynamic instability. Because at every swing, if you apply some force at exactly the right point, the deflection, the motion of the swing gets larger and larger and gets out of hand. Another well-known example of a positive feedback mechanism causing dynamic instability are childbirth contractions. When contractions happen, they release a hormone, oxytocin, which causes more contractions. Another example is thermal runaway, exothermic reactions. They require heat as a catalyst, but these exothermic reactions produce heat themselves, giving rise to more heat, more catalyst, and more reaction. And operational amplifiers in electronics also use the concept of positive feedback. Now, the way systems theory looks at stability is based on the dynamic behavior of system properties under external inputs. And this dynamic behavior is studied using differential equation in the continuous case or difference equations in the discrete case, considering always at least one input x and one output y in function of time, symbolically represented in that system diagram. Now, a system is defined to be dynamically stable if and only if a bounded input results in a bounded output. And if we would describe that system with a simple first-order model, you would have, for the continuous or discrete case, a differential or a difference equation, first order. And so stability requires that the coefficient, the feedback coefficient, needs to be negative. Because if that's not the case, you have a positive feedback which can cause an instability. Coming back to the Tacoma Narrows Bridge and the aeroelastic flutter which caused its destruction, well, basically in this case the input is the force of the wind and the output is the deflection or the energy of the bridge. Now, if you look at a simple first-order equation, the dynamic instability in this case is indeed caused by a positive feedback mechanism between the deflection of the bridge or the body and the force of the fluid flow, the wind. And the increase in body deflection, the increase in energy in the bridge is proportional to the external input, the force of the wind or the fluid. And the point why it started to collapse was there was zero net damping. So the coefficient causing feedback was zero. There was zero net damping, which allowed the energy of the wind to accumulate in an unbounded way in the bridge. And you see it represented here. Though the wind was constant and not unbounded, it got accumulated, and therefore the deflection and the energy in the bridge became unbounded. Now, if we take the other example of childbirth contractions, we consider the childbirth contractions and its intensity as the output, the hormone oxytocin as the input, and of course here's another feedback mechanism. The feedback mechanism in this example, causing the dynamic instability, is that the contractions themselves release more of the hormone oxytocin, and therefore the coefficient, the feedback coefficient, is positive, not zero, it is positive. More contractions cause more release of the hormone, more contractions, more release, and so on. So if we in this case have an initial activation of a release of the hormone, the initial activation, the input may become zero, because once the process starts going, it is self-sustaining, it is unstable, and you get more contractions, more release of oxytocin, more contractions. Now, this dynamic behavior in systems theory is typically studied for operations of systems. It is typically used to study the stability and the dynamic behavior of the operations of mechanical systems like constructions, buildings, towers, vehicles, electrical systems like amplifiers, generators, hydraulical systems, pumps, engines, compressors. But it is not used to study the dynamics of a system design, the evolution of a system design. It is not studied for the design cycle. So what normalized systems theory tries to do is to use systems theory, stability, to study the evolution of a design, the evolution of an artifact like an engine and information system. Now, can we look at the design cycle as a dynamic system? Well, then we have to consider the function construction transformation. The design cycle can be considered as a transformation of the functional requirements into constructional primitives or artifacts. And so we could have a number of requirement specifications, being the inputs X, and a number of versions of artifact modules, being the output Y. Now, if we simplify these in general high-dimensional vectors to scalars, being the input is the amount of specifications at a certain point of time, and the output is the amount, the total amount of versions of modules at a certain point in time, then we can see that we have a dynamic system to study. And then we can ask ourselves, is there a feedback mechanism? Is there a possibility for a dynamic instability? And indeed there is, and that is due to the change rippling through the system. If you perform a change in an artifact, in a technological artifact, you get ripples. The change ripples through, it will cause other ripples, causing other ripples, etc. And that is the feedback mechanism, the positive feedback mechanism, if you look at the design cycle as a dynamic system. We can clarify this with an example, for instance, the mighty Saturn V. The mighty Saturn V was capable of delivering 120 metric tons to Earth orbit. Now, suppose you would want to increase the payload, you could say, well, we need to increase the number of engines. So we could add, for instance, an additional F1 engine to the first stage. Now, if we would add such an engine, of course, we would also have to add a fuel line to that engine. We would have to have a more powerful fuel pump. because it would now have to serve 6 engines instead of 5 engines, we would need a larger fuel tank, because we would need more fuel, and the larger fuel tank would become heavier, more fuel, the pressure would be larger on the various parts, so we would need a stronger fuel tank, and probably we need to adapt the shape of the fuel tank because the dynamic vibrations and characteristics would change as well. And it might be possible we need to enlarge the interstage, the second stage, maybe even the heat shield. So basically we would have to design a complete new rocket. So if we look at the design cycle as a dynamic system, these rippling of changes is a positive feedback mechanism which can cause instability. Not just if we want to change, increase the functionality of the artifact. Also, this might happen when we have to replace a part of it. Consider, for instance, this is a real example, a racing bike which, when 18 years old, needed to replace the gear handle. And you see the gear handle there with the small ellipse. It's a very small part. However, that gear handle distinguished 8 gears, and the manufacturer didn't make any more gear handles for 8 gears, but only for 7 or 9 gears. Now, if you use a handle for 7 or 9 gears, you have to use a gear block in the back as well for 7 or 9 gears. Now, if you change the gear block, you need to change the gear cabling and probably also the gear block in front and the chain and many other things. And once again, basically you need to replace the whole racing bike, probably. So ripples, changes rippling through technological modular artifacts are an important issue, causing a positive feedback mechanism and therefore dynamic instabilities if you consider the design cycle as a dynamic system. And so you can do that for the software design cycle as well. You consider the software transformation from functional requirements to constructional primitives, artifacts or module. And consider once again a simple system diagram. And so the requirement specifications would be the inputs X at a certain point in time, and the versions, the total amount of the versions of software modules would be the outputs Y. And once again, the positive feedback mechanism, which can lead to dynamic instabilities, is created by ripples caused by the changes. And in traditional evolving information systems, these changes can be applied, they are applied on a regular basis, so you really have a discrete time variable k, and they do cause ripple effects. Now, of course, you have to very well define what that transformation is, what the transformation is from the input to the output. Well, in a basic form, you could say that requirements, specifications for an information systems are basically data entities and action entities. Data entities representing data, for instance, like an order with a reference number, a product ID, etc., an invoice linked to the order with a number and an amount and stuff. And you would have also actions item, action functions, processing something, doing something, like creating an invoice, processing an order, sending an invoice. So at the left-hand side, we have the specifications, the requirements in a very basic form. And on the right-hand side, we would have software primitives, being a data structure in a procedure language or a class with a number of attributes, which is the transformation of the data entity we want to represent. And so the transformation of the action is a processing function or a class with a main method. For instance, actually performing the creation of the invoice, processing the order, or sending the invoice, for instance, by email. Now, in this basic form, these things look similar at both sides, but they are not. At the left-hand side, we have conceptual data entities, conceptual actions, And at the right-hand side, we have software primitives, data structures, classes, methods. But because the transformation is so basic, they seem more or less similar. But nevertheless, at the left-hand side, these are very basic requirements, because you could also keep track of the invoices and their various instances with pen and paper, for instance. Now, if you would have a change at the left-hand side, which is an external input, an additional requirement, for instance, adding another attribute for the order, then it is conceivable that you don't only have the transformation of that input, that you don't only have an output based on that input, but that there would also be an output due to the positive feedback mechanism of ripples. The positive feedback mechanism in the actual software primitives, where you would have to change, for instance, certain methods or functions in handling or creating the order data structure and dealing with this additional attribute. This would be changes that would be caused, that would require new versions of modules, of software modules, due to the positive feedback mechanism of ripple changes. Now, if you consider ripple effects in a growing and evolving modular structure, it can be a big deal. Consider, for instance, at the right-hand side symbolically a representation of all the versions of functions, methods, data structures of software artifacts or primitives, and at the left-hand side your entity relationship diagram or flow diagram representing the data entities, the tasks, the flows you have to perform. Now, if you look here, you would see that you could get a dynamic instability caused by positive feedback between the modular structure of the versions of the modules, and that you would actually have a positive feedback factor A, but a positive feedback factor A not in the total amount of versions of software modules, but in the marginal additional amount of versions of software modules you would have to make, to produce for a certain set of requirements. And so you have indeed a positive feedback factor, which you shouldn't have, but not even for the total amount of software modules, because it would be logical and not harmful that if you would have an unbounded amount of growing requirements, that you would have an unbounded amount of software modules. But because the system grows, you would have an unbounded amount for the number of additional modules you have to make. So if the structure grows, it's not just the total amount of modules and versions of modules that becomes unbounded, it is the marginal amount that becomes unbounded. Because suppose you have a pretty constant stream of additional requirements, then you would have a pretty constant growth of versions of modules, of software modules, but you would even have a growth of the marginal amount of additional software modules at any point of time. And this growth, of course, causes that the actual growth of the total amount of software modules becomes more than linear, and that even the total amount of additional software modules becomes unstable as well, due to this positive feedback mechanism of change ripples. Now, the next part of NST is based on saying, look, we want to avoid these dynamic instabilities. We want to avoid this positive feedback, these dynamic instabilities in the software design cycle. We want to deplete the rippling through of changes. We want damping or depletion of these ripple effects. Now, as these ripple effects create combinations of multiple changes in the software modules for every functional change, we call these instabilities or ripple effect combinatorial effects. And demanding systems theoretical stability, demanding that there is a damping or depletion of those ripple effects, that we don't want these dynamic instabilities, that will lead to the derivation of principles, design principles for software in line with existing heuristics. And so adhering to these principles, which will be detailed in the next lecture, avoids dynamic instabilities, meaning that these principles are necessary. However, that does not yet mean that they are sufficient to obtain software which is dynamically stable, which does not contain dynamic instabilities due to positive feedback. Now, of course, you can always send remarks or questions to me. Thank you.